As I hope you remember that when we spoke about the meaning of this density function, we spoke that the area under this graph must represent the probability that the random variable takes some values, right? So values inside some interval. If we calculate the area under the whole curve of the density function, it must be 1. So if the base of this rectangle is b minus a, and if the height of this rectangle is exactly 1 over b minus a, when we multiply them, we will get 1. And if you want to find, for example, the probability that the random variable takes values between 0 and 2, for example, in this interval, then probability is going to be 1 over 10 divided by, multiplied by 2, which means that this is going to be 20%. Or here, when we want to calculate the probability that the random variable takes values between 8 and 6, it's also going to be 20%, right? So 2 multiplied by 1 over 10. So it's very simple distribution, widely used when you want to represent equally probable outcomes. Basically, the outcomes in this interval are equally likely as the outcomes in this interval or anywhere else. And many kind of random number generators, they also use this uniform probability density in order to give you some random variable. So the properties, I'm not kind of deriving these things. You know how to get, for example, this cumulative distribution function. We need to integrate over this density function. So the cumulative distribution function is given here. So it's x minus a, where x is the value of a random variable divided by b minus a for these values. And as you know, 0 if x goes to minus infinity and 1 if x goes to plus infinity. So regarding the characteristics of this distribution, so the average or the mean or expected value is simply a plus b divided by 2. So it's something natural, right? So if I go to this interval, so what's the expected value of this random variable y, given that y is distributed on the interval between 0 and 10, and all outcomes are equally likely. So that's exactly in the middle. So 0 plus 10 divided by 2, which is 5. So it's natural. And regarding the variance, so we spoke how variance is calculated. We need to integrate over the expression x minus expected value of x multiplied by the density function. So basically, I don't give you the derivation of it. So the variance is given by this number. Once again, basically, if you don't remember something, so at this moment, at least for me, and at the moment of bachelor studies, I don't force you to know all these derivations. So everything is available. You can just go to the internet. You can Google something like uniform distribution. You can open. So like there are two, discrete and or continuous. So we speak about continuous. You can just go there, and basically in any Wikipedia article regarding any kind of distribution, here on the right you can find, well, this is the PDF of this distribution, this is the CDF, this is the mean, this is the variance. So everything is available. And if you will go, I don't know, to some master studies and probably will have some course, like advanced course in statistics, probably you will be expected to derive all these formulas. So I don't expect you to do this. So here is an example. Suppose that the arrivals of customers at the checkout counter follow a uniform distribution. And we know that during a given 30-minute period, one customer arrived at the counter. So basically, we know that 1/30 is the probability that one person would come in either in any minute. So we need to find the probability that the customer arrived during the last 5 minutes of the 30-minute period, and also find the probability that the customer arrives between 17 and 23 using this uniform distribution. So please try yourself. You know how to calculate probabilities for continuous random variables after the exercise session, and then we will discuss. So give me these answers. What is the probability that the person comes in the last 5 minutes, and what's the probability that the person comes between these 17 and 23 minutes? The values of between 25 and 30, we can integrate this density function. So the density function is 1/30. And so this integral is simply x/30. And then we plug 30 and 25 here, and we have 1/6. If you want, you can use integrals, of course. So using the same methods, we can calculate the probability that the customer arrives between 17 and 23 minutes. What is this probability?
1/5.
It's the same, 1/6. Because it's also 5 minutes, right? And we know that the probabilities of equal intervals for the uniform distribution are equal as well.
I somehow calculated that it is 6, not 5.
Yes, it's 6.
Oh, guys, yeah, it's 23 minus 17. Yes, it's 6. It's typo. I guess it's typo. Sorry. Yeah, you're right. You're right. I wanted to give you the example that it's those are equal, so it must be okay. Yeah, you're right that this is 1 over what you said. It's 6/30. It's 1/5. Yes.
Yeah.
Yes, but I wanted to demonstrate it, so it's my fault actually. Must be 17 and 22, just to show you the sense that those are the same. But in principle, yes, you're right. If you used this as a 5 minutes interval, then it's gonna be like this: 17, 23. It's 23 here. It's 17 here, and then we have 23 here, we have 17 here, and we have 1/5. Yeah, so my bad. Okay, so the uniform distribution is something simple, and if you are attentive enough, and if you don't do these mistakes, then everything must be okay. Both approaches, as you know, are possible. Either you use this CDF or you use the integral. The results are going to be similar. So now another very popular distribution. So this distribution is used in finance, for example, when you want to predict the probability of some extreme losses. Like what is the probability that we lose almost all our investments, something like this. So some catastrophic events. So it is the exponential distribution, and we define this exponential distribution in the following way. So it has the following density function, and it has the parameter lambda, which must be positive. I hope you remember from the discrete distributions, we spoke about them here, that there is also another distribution with the same letter used for the density function. It's also lambda, and they are somehow connected. This Poisson distribution, which is the probability of number of rare events, so that's a number of rare events. Yes, hi Alexandra. For the exponential distribution, this lambda has something similar, and they are connected. So the exponential distribution is used to model the length of time between occurrences in this homogeneous Poisson process. So like in Poisson, we calculate the probability of the number of rare events. And in exponential distribution, so it was derived to measure the time between these occurrences. So how long does it take between like one occurrence of some rare event and second occurrence of rare event? That's how this distribution has been derived. But as I said, sometimes this distribution is used in finance to calculate the probability of some large rare losses. And the graph of the density function is shown here for different values of lambda, because lambda is the only parameter that kind of affects the shape of this distribution. So we see that the density is kind of decreasing, and so the area, the most of the area under this curve is contained between 0 and some small number of x, and so when we move x farther to the right, so this probability kind of decreases very fast. So let's see the properties. As for the uniform distribution, the cumulative distribution function, when we integrate the density function, is given by this formula for any x which is positive. Why, as I said, we measure time. That's how we derive this variable, or when we measure money, like losses, they are also positive values. The expected value of this distribution is 1 over lambda, and the variance of this distribution is 1 over lambda squared. So, another example for you. The time is minutes between the arrival of successive customers at the post office has exponential distribution with lambda 0.2. So, two questions. What is the expected time between arrivals, and what is the probability that the person, so one person comes at 12:30, what is the probability that the next person arrives on or before 12:32 and after 12:35? So it's kind of like less than 2 minutes or more than 5 minutes. Okay, so that's how we calculate these probabilities. By the way, any questions? So, kind of conceptually, we apply all the things that we already know from the previous week, how to calculate probabilities of for continuous random variables. Now we are just working with some special probability density function or cumulative distribution function, depending on our needs. But as you know this, no need to do the integration. You see that we are fine without integration in either case. So now the next very popular distribution is a normal distribution. You probably have heard about this normal distribution a lot, maybe not, but still it is applied in many fields. So we call the random variable to be a normal probability, or the normally distributed function when the probability distribution is given with this formula. And it's disaster, right? Because it looks terrible. It's very difficult to remember formula and compare to the previous ones. But that's how we define this probability density function. If you look closer, we have two parameters in this distribution. So there is x, as usual, because x must be here. So pi is just a constant, e is just a constant. These are just two numbers, and we have two parameters. It's mu and sigma. And you know what is mu and you know what is sigma. Mu is the expected value, sigma is the standard deviation, and sigma squared is the variance. So basically the density function of a normal probability distribution depends on the expected value of this random variable and on the variance of this random variable. Good news are, for this course, you don't need to remember this probability density function. So you just need to be able kind of to search the internet and to find this formula if it's necessary. No need to remember this. Second good news, it's very painful to calculate the integral of this function. And the good news are that you don't need to calculate this integral. So how to deal with that, we will discuss a bit just in a minute. So the density function, the graph of the density function looks like this bell, and the shape depends on mu and sigma. So basically, the greater is the variance, so the larger is the sigma, the wider is this bell. So if the bell is very narrow, like this one, like this solid line, it means that the sigma is very small. The variance of this random variable is small. If sigma is large, then you will have something like this dashed bell, which is kind of stretched from left to right. That's how it depends on sigma. And mu identifies the center of this bell. So for these three distributions, mu is 0. Mu is 0. But if mu is something different, so you move this bell to the left or to the right, depending on the expected value. So CDF. As I said, good news, we don't need to calculate the integral. Basically, the CDF is defined just as an integral of this function. There is no better formula to calculate CDF. That's why for this course, we will be using the formula in Excel, which is normdist. I kind of invite everybody to do this. There are also some statistical tables, but personally, I don't prefer these statistical tables because it's something old-fashioned. We all have now the computers, some calculators, something else. So we must be able to do this with the help of software. I will demonstrate you how to deal with that, how to use this function, and you also need to know how to work with that. And as I said, the expected value is just a mu, and the variance is just sigma squared. So two parameters which are contained in this density function, mu and sigma. So now, here is an example. Suppose that the daily change in Standard & Poor's 500 index, we define it as x, follows a normal distribution with mean of 1,000% per day and standard deviation 100% per day. We need to find the probability that this index will decrease in a given day. So how to translate this in the probability language, what we are looking for, if this index will decrease. look, X is the daily change, right? So by how much some stock index changes. What must be the value of change if we speak about decrease in this index? So how should I write this probability? Probability that X is what?
What is norm dist in Russian Excel? Could you?
I will tell you. So let's first answer this question. What must be the probability that X is what? According to this question. Okay, guys, so when we say that something decreases, what is the value of change for this something? So we have this S&P 500 index, and if this index decreases, it means the daily change is how much? Or in which interval, at least? Come on, guys, it's 2 months of studies and you're already tired. What's happened to you?
Yes.
But there are 2 months more till the end of the semester. So what's gonna be in November?
The strongest will survive.
Yeah, I agree. But that's a simple question. Come on. So we have an index. So it's just some number. When this number increases, what are the changes? And when the number decreases, what are the changes?
The percentage of.
Okay. I mean, so like we are speaking about the interval from minus infinity to plus infinity. So tell me, when we speak about X as a change in the value of this index, what must be the X in which interval from minus infinity to plus infinity this X must be in order to say, well, the index increases? And in which interval from minus infinity to plus infinity X should be to say, well, X decreases. Oh, not X, sorry, index decreases. And what must be X to say, well, index is constant, no change in the index. Okay, maybe the last question is the crucial here. What should be X? X is the daily change. What exactly X should be equal to in order to say index does not change? What should be the change if you say that something does not change? X must be 0. X must be 0. Okay, if index decreases, then what's the relation of X to 0?
With minus.
X is less than 0. If index increases, what must be X? X is greater than 0. Perfect. So we are looking for the probability that X is less than 0. Right? That's what we are looking for. Okay, and the second question that we need to analyze, find the worst outcome in S&P 500 return that will not occur with probability 99%. So this is something more difficult to understand. We know that some probability here must be equal to 0.99. So we know the probability exactly. What are we looking for? The worst outcome in this return that will not occur with probability 0.99. How should I write this inequality? X is
or equal 0.
Wait. So it's not 0, of course. We are looking for this number. Now, look, now we need to be very careful. X is less than something with probability 99%. Means that it's from minus infinity to this number with probability 99%. There is 1% of the best outcomes, of the best possible outcomes. But we are looking for this, the worst outcome that will not occur with probability 99%. It
But
means
it
that
said-
99% must be better than this, right? It means that we must change this sign. X must be greater than something with probability 0.99.
But it is said that we should find the probability that the return will not occur.
No, find the worst outcome in this return, right? So in X, basically, that will not occur with probability 99%. So the worst outcome means that it's something very, very negative. If X is distributed from minus infinity to plus infinity, we are looking for something very negative that will not occur with probability 99%. So it means that it will occur with probability 1%, right? So from minus infinity to 1%, it will occur. And 99% cases, it will be better. So from this number to plus infinity, it will be better. So that's why I wrote it like this. And this something, so the question sign is basically it's some number. And how do we call this number? Do you remember? When we know the probability and we are looking for the number that gives us exactly this probability. How do we call this? No. Okay, I will rewrite this a little bit. So it must be like this. Must be equal. So from here, I'll be able to write that this is less than this number with probability 1%. Okay, so now, do you remember when we are looking for this, when we are looking for some special value of X that gives us some probability, how do we call this X? Where was it?
A variable, wait.
We call this quantile. We call this quantile because we are looking for the special value of X that yields us the value of distribution function exactly equal to this. Okay, so don't forget about this. This is a quantile. So I must write it like this. So it's 1% quantile of a normal distribution. So what is this? To the sign here. Okay, so now when I know that this is a quantile, I'm able to use it here. And be careful, here it's not 99% quantile, it's also 1% quantile. Okay. Okay, so let's first understand how to calculate this, and then I will also demonstrate you the meaning of all these things. Maybe it's better to do this vice versa. Okay, so one thing. Just a second. Let me think. Okay, so I will take it from the book. It would be faster. Find some graph of the normal distribution. This return, right? So the change in Standard & Poor's 500 index. And we know that here in the center, there is this line. There is a value of what's given in the setup. It's 0.001%. So 0.001%. So that's exactly in the center here. When we speak about the negative change, we are looking for this. So basically 0 is somehow to the left of this number. So maybe close to the left, maybe far from the left. We don't know yet. And we are looking for this. So in the first question, we are looking for this. So I'm taking 0. As a possible value of my random variable. So it's 0%, right? And I'm looking for the probability that my random variable is going to be from -infinity to 0. So negative, basically. So I'm looking for the area under this curve from -infinity to 0. So which means, how can I draw it? I'm looking for this area. So that's what I'm looking for. That's my first question. Nothing is different from what we have been discussing in general about the continuous random variables. So the continuous random variable and this probability identifies the area under the graph of PDF. So that's exactly the same as we do right now. So the second question is a bit more tricky, because what we want to know in the second question. In the second question, we want to do the following. We know that there is, once again, the 0.001 in the middle, so this one, but we want to calculate what must be the value of x such that this area, in this case, this area is going to be a very small area, this one. So we know that this area must be equal to 1%. So this probability that x is less than something, is less than small x, like this one, equals to exactly 0.01. And I don't know what is this x. I'm looking for this x. This is the quantile, so that's what I want to calculate. I want to calculate this small x. I don't know what is this. And 99% is greater than this return, right? So it's either kind of negative, but not that negative, not that bad, or positive. you must clearly understand what we are looking for in both cases. In one case, once again, we are looking for the probability. We are looking for this area. That is what is not known. In the second case, so I'm looking for the probability that my x is less than 0 and this is not known. In the second case, I know the area exactly. It must be 1% or 0.01. I don't know what x cuts me this area. This is the quantile. This is just a probability. Is this clear? Or maybe I need to, I don't know, tell it somehow differently. I'm always saying that this is important, but believe me, this is really important. You don't need to confuse these two things. Why after this class we are going to use this almost every time, these two differences, quantile and probability. Those are inverse functions, basically. Okay, do you have any questions? Okay, good. Then let's do the practical things. Well, that's what we need to do. If we want to calculate this probability, that's what we need to do. We need to evaluate this integral from -infinity to 0 of this very nasty thing, which is hard to evaluate. So what should we do? We should go to Excel, and that's what I want all of you to do. Please open Excel if you have. If you don't have, well, try to have it, or try to find some other way to calculate this probability. Basically, there are some calculators on the internet that give you the same opportunity. So I would prefer Excel. Yes, so Vlad asked me about the Russian version of this function. Let me think. It must be something like norm dist, I guess. I worked in Russian version of Excel too many years ago, but it must be something like this. Check if you have this function. Vlad, do you have it?
I don't
Norm.
have norm disk in my.
You just need to type like this, equals
Norm,
and it will give you the list of functions that.
Yes.
I haven't got it.
Norm over, norm rasp, norm.
Okay.
norm over
Yes, wait.
over.
Norm rasp. Yes, that's what you need. Norm rasp.
Uh-huh.
For this case, you need norm rasp.
Okay.
Okay, so let's write mu is 0.001%, right? Sigma is 0.01%, and our small x is 0. So I prefer to do it in this way. So now, what is the probability that our small x is less than 0? So you do the following. You type, if you work in Russian, so you write this norm. Okay, I do the same. And then I select from here this norm dist. In Russian, it's going to be norm rasp. Unfortunately, I don't know how Chinese version of Excel looks like. So guys, those who work from China, try to find what is the appropriate way to calculate this. So, and then look, then there are 4 parameters for this function. When you double click on this function, it asks you to type all these parameters. So first of all, you need to type this small x, which is 0. Okay, you just press on this, then depending on the on the syntax of your Windows system, it's either comma or semicolon, depending on what you have. So look at this. Just it must help you, like what to put, comma or semicolon. So you choose mu, then you choose standard deviation, and then the last important thing, you need to, as the last parameter, you need to put 1 or true, or in Russian it must be not
Истина.
true, but how, like истина, yes, but it's better to write 1. That's okay. I mean, if you put 1, that's totally fine. Okay, and then when you press enter, you must have something like 0.46. Okay, so once again, a bit faster. You type equal, then you start, if it's Russian version of Excel, you start typing norm. If it's Chinese version of Excel, sorry guys, I don't know what is in the Chinese version of Excel. So you must look for this yourself. So then you choose this norm dist or norm rasp in Russian version. Then you type x, semicolon or comma, depending on the syntax, mean, sigma, and then 1. Instead of истина or true, you can write 1, and then you press enter and you have this 0.46. So what does this mean? It means that the probability that this index S&P 500 will decrease is 46.01%.
It doesn't calculate, I don't know why. Norm rasp.
Запятые
With,
используй, запятые.
Yes, so instead of these semicolons, probably you need to put commas only.
No, it says I need to use semicolons, but
Okay.
anyway.
No, it's like not 0.1, it's 0.01.
Ah, yeah. So,
Ah.
yes, I have English version of Excel, so that's why I'm using this 0.001. If you use Russian version of Excel, of course, you must put 0.001%. Yes. That's why if you study in English, so probably it would be better to kind of to switch all of your software into English version just in case. Okay, guys, how many of you have this result, or at least successful?
I got it the same.
Zhao Rusuan, do you have the answer?
Yes, I tried to excel this.
Okay. So you found what's going on in the Chinese version of Excel.
Yes.
Perfect. Guys, anybody else? So as you can understand, I'm paying too much time because you really need it. So
I also get it.
another option, basically, if you don't have Excel or if you have no idea how to work with that, you can Google something like normal distribution calculator. There are a lot of them. So I don't know, like this. Look, specify parameters 0.001, standard deviation 0.01, and then the question is, so what we are looking for below 0. Bam, here is the probability 0.4602. Basically, if you prefer, you can use this, but I highly recommend you to do Excel. Why? Because in Excel later on you will be able to calculate many different things, but for this moment, if you are not sure about Excel, well, Just try to find some appropriate calculator on the internet. It will give you the same. So now the second question, how to find this x, which cuts us 0.01% probability. So now we do something different. So p is equal to 0.01. Again, according to the syntax, you want to put comma there, probably. And then we're looking for this x 0.01, which is the quantile of a normal distribution. So in this case, in Russian version of Excel, you will use something like norm ober. I guess there is something like this. Check it. So in English version, it's norm inverse. And look, the parameters are almost similar, except for instead of x, you are using probability. So I'm taking this probability here, then I'm taking mu, and then I'm taking sigma. And that's it. No need to specify whether it's cumulative distribution or not. That's all, and we have this. So if I change it to percent, it's going to be like this. It's just a format. So you have initially this number. If you want to change the format, you press percent, and then you increase the number of decimals. That's it. So once again, the function is norm inv or norm ober in Russian version of Excel. You put their probability, you put their mean, and you put their sigma. And then you must have something like this. In percent or without percent, it's gonna be this. Minus 0.3022. Okay, who has this answer? So here, 0.022%. So basically, in 1% of the worst cases, you will have the return which is less than 0.022%. In 1% of the worst scenarios. In 99% of the cases, your return is going to be higher than this one. Okay, so I will send you this file with these formulas. If you open this in your version of Excel, in Russian, Chinese, any other version, so it will change you these formulas according to what you have in your version. I need to speed up a little bit because we have 2 minutes and 3 slides. There is something that is called standard normal distribution. If we have a random variable x, and this random variable is distributed according to the normal distribution with mu and sigma squared, so this is the way how we write that x has a normal distribution with this mean and this variance. Then we can transform x according to the following formula. If we subtract mean and divide by the standard deviation, then we will get a random variable z, and this z will have a standard normal probability distribution with mean 0 and standard deviation 1 and variance 1, basically. You had the same example in your exercise session. There was a general case, proof that some random variable transformed in this way has always variance 1 and mean 0. You had it, you must have had it in your previous exercise session. So apply it to the standard normal distribution, that's the same. So x, if you want to come back to x equals to mu plus sigma z from this expression. We usually denote the density function with this small Greek letter phi because it's some special distribution. That's why we have a special letter for it. And the probability that, so the cumulative distribution function we denote as a large phi or capital phi here. And that's actually what I showed you in the example. When you have the standard normal distribution and when you have the graph of a density function, then given some value zp, the probability that our random variable z is less than or equal to z is this area, and that's exactly this cumulative distribution function phi. Okay, so there is some empirical rule which is widely used, applied to the standard normal distribution. If the distribution is approximately normal, then the 68% of the measurement is going to be between mu plus minus sigma. 95% of the measurement approximately will be within the interval mu plus minus 2 sigmas, and almost all of the measurements are gonna be within the interval plus minus 3 sigmas. Why? Because if you calculate these probabilities, you will get exactly this. You will get exactly these numbers. So I need to stop here because we are running out.